The black hole at the heart of the Milky Way for most of human history. The Milky Way was not a galaxy. It was a presence. A pale river of light stretching across the night sky, familiar enough to be named, mysterious enough to resist understanding. People told stories about it, worshipped it, navigated by it, and wondered at it, but never imagined that this glowing band was a vast structure of hundreds of billions of stars, or that it possessed a center at all. The night sky appeared flat, decorative, a backdrop rather than a place. And somewhere within that luminous haze, something profoundly powerful already existed, exerting its influence silently, shaping the destiny of stars long before humans learned to ask the right questions. From Earth, the Milky Way feels intimate. It arches overhead on clear nights, cutting the sky in half, constant across generations. Yet this familiarity hides a fundamental deception. We are not observing our galaxy from the outside, like astronomers do with distant spirals captured in pristine photographs. We are embedded within it, trapped inside its disk, surrounded by dust and stars that block our view in nearly every direction. Trying to understand the Milky Way from our position is like trying to comprehend the shape of a city while standing in a narrow alley, hemmed in by walls, able to see only fragments at a time. For thousands of years, humans naturally assumed that what mattered most must lie close by. The stars wheeled overhead, planets wandered across the sky, and the Milky Way shimmered like a celestial scar. But there was no obvious center, no anchor point, no sign that one region mattered more than another. If anything, the night sky suggested symmetry and balance, not hierarchy. The idea that the galaxy had a heart, let alone one that dominated everything around it, simply did not exist. Even when astronomy began to transform into a science, the illusion persisted. Early telescopes revealed more stars, not structure. Each improvement in technology deepened the mystery instead of resolving it. The Milky Way grew richer, denser, more crowded, but no clearer. Dark lanes of dust cut through the glowing band, obscuring what lay beyond, as if the galaxy itself were concealing something. The center, whatever it was, remained hidden behind veils of interstellar matter, unreachable by visible light. What makes this ignorance remarkable is not that humans failed to see the galaxy's center, but that the center never announced itself. It did not blaze like a beacon. It did not dominate the sky. It did not pull our solar system into violent motion. From our quiet orbit far from the core, life unfolded under the illusion of cosmic calm. Seasons changed, civilizations rose and fell. And all the while, something immensely massive and fundamentally alien remained at the heart of our galaxy, exerting its influence across tens of thousands of light years without ever revealing its true nature. Only in hindsight does the scale of the misunderstanding become clear. The Milky Way is not a gentle band of light, but a rotating disk more than 100,000 light-years across. Its stars do not drift randomly, but follow ordered paths around a common gravitational center. Every orbit, including that of our Sun, is part of a vast cosmic dance choreographed by something unseen. Long before humans understood gravity, long before the concept of space-time, that choreography was already in motion. The power of the galactic center lies not in spectacle, but in inevitability. It does not need to shine to dominate. It does not need to announce itself to matter. Its presence is written into the motions of stars, the structure of the galaxy, and the slow, steady rhythms that govern cosmic time. For billions of years, it has shaped the Milky Way from within, unseen and largely unknowable, while life on at least one small planet unfolded in ignorance of its existence. This contrast is what makes the story so compelling. Something so central, so influential, remained hidden not because it was distant, but because it was too deeply embedded, too enshrouded, too subtle in its effects to reveal itself easily. The galaxy felt familiar because we were immersed in it. It felt harmless because we lived far from its most extreme environment. And it felt understandable because humans naturally project their own scale onto the universe. assuming that what cannot be easily perceived cannot be overwhelmingly powerful. The slow realization that the Milky Way has a heart, and that this heart is unlike anything in ordinary experience, represents a profound shift in perspective. It forces us to confront how limited our intuition is when dealing with cosmic scales. It reminds us that familiarity does not equal understanding, and that some of the most important forces in the universe operate quietly, shaping reality without spectacle. At the center of our galaxy, something has always been there. It does not care whether it is observed or understood. It bends the paths of stars, sculpts the flow of matter, and anchors the structure of the Milky Way itself. For most of human existence, it was nothing more than an absence, a blank spot hidden behind dust and distance. And yet, from that hidden place, it has been shaping our cosmic home since long before the first humans looked up and wondered what the Milky Way was at all. For centuries, the Milky Way was studied as a pattern rather than a place. Astronomers cataloged its brightness, traced its arc across the sky, and debated its nature. But the deeper question of structure remained stubbornly unresolved. The difficulty was not a lack of curiosity or intelligence, but a fundamental problem of perspective. Humanity was trying to map a system while standing inside it, with no clear vantage point from which the whole could be seen. Early observers naturally assumed that what they could see most clearly must be closest and therefore most important. The densest regions of stars appeared to surround Earth, giving the impression that our position might be central, or at least typical. Without reliable ways to measure stellar distances, the sky collapsed into a two-dimensional illusion. Bright stars felt near, faint stars felt far, and the Milky Way looked like a thin, luminous shell wrapped around the world rather than a vast disk extending tens of thousands of light years in all directions. As telescopes improved, the confusion deepened instead of fading. More stars filled the field of view, not fewer. The Milky Way became thicker, brighter, and more complex, but its overall shape remained elusive. Dark gaps appeared within the glowing band, regions where stars seemed to vanish entirely. Some astronomers believed these voids were true holes in the stellar distribution, places where stars simply did not exist. Others suspected that something was blocking the light. But the idea that enormous clouds of interstellar dust could obscure entire regions of the galaxy was slow to gain acceptance. Distance was the central obstacle. On Earth, distance can be inferred through perspective, motion, and familiarity. In space, those cues collapse. Stars are so far away that their motion against the background sky is almost imperceptible over a human lifetime. Without knowing how far away stars truly were, astronomers could not tell whether they were looking at nearby objects spread thinly or distant objects packed densely together. Every attempt to draw a map of the Milky Way depended on assumptions that were difficult to test and easy to get wrong. This uncertainty bred wildly different models of the galaxy. Some imagined the Milky Way as a relatively small system with the Sun near its center, surrounded by a modest halo of stars. Others proposed much larger structures with the Sun embedded far from the core. Each model could be made to fit limited observations, and without decisive evidence, debate persisted. The galaxy became a mirror, reflecting the limits of human measurement rather than a clearly defined object. Living inside the Milky Way introduced another profound complication: obscuration. Vast clouds of gas and dust filled the galactic plane, absorbing and scattering visible light. These clouds are not subtle. They are thick enough to hide entire star fields, entire regions of the galaxy, from optical telescopes. To early astronomers, these dark lanes looked like absences rather than obstructions. The idea that the galaxy could be hiding itself was deeply counterintuitive. It required accepting that what was missing from view might be more important than what was visible. As a result, attempts to locate the galactic center repeatedly failed. The brightest regions of the Milky Way did not point unambiguously to a central hub. Star counts varied depending on direction, but dust distorted every measurement. Looking toward, the inner galaxy felt like staring into fog, where landmarks dissolved and depth became meaningless. Astronomers knew they were missing something, but could not tell what it was or where it lay. This frustration was not merely technical, it was philosophical. Astronomy had long relied on the assumption that the universe, while vast, was ultimately legible. Patterns could be uncovered, structures identified, and positions determined with enough patience. The Milky Way challenged that belief. It suggested that some systems resist understanding not because they are chaotic, but because the observer is trapped within them. Even analogies failed. Mapping the galaxy was often compared to trying to map a forest from within, but even that fell short. In a forest, one can eventually climb a hill or leave the trees behind. In the galaxy, there was no escape from the disk, no way to step outside and look back. Every observation was filtered through the same crowded, dusty plane. The breakthrough, when it eventually came, would require abandoning intuition and embracing indirect reasoning. Instead of asking where the galaxy looked brightest, astronomers would need to ask how stars moved, how clusters were distributed, and how gravity revealed structure without light. But before that shift occurred, decades passed in uncertainty. With each generation refining measurements without resolving the fundamental question of where the Milky Way truly centered itself. This long period of confusion serves as a reminder of how deeply perspective shapes understanding. The galaxy was not hiding its structure out of malice or mystery, but because human senses and tools were tuned to scales far smaller than the system they were probing. The Milky Way exposed a humbling truth. Being surrounded by something does not make it easier to understand. Sometimes it makes understanding almost impossible. Only by confronting these limitations did astronomy begin to change. The realization that the problem lay not in the galaxy but in the observer marked a quiet turning point. To understand the Milky Way, humans would need to let go of familiar ways of seeing and accept that the universe does not arrange itself for human convenience. The path forward would be indirect, frustrating, and slow, but it was the only path available. This era of uncertainty also shaped the culture of astronomy itself. It rewarded caution over confidence and patience over bold claims. Each failed attempt to define the galaxy's structure reinforced the need for better tools and deeper humility. Astronomers learned that precision without perspective could mislead just as easily as ignorance. Measurements taken with exquisite care still produced distorted conclusions when the underlying assumptions were flawed. In that sense, the Milky Way became a teacher, forcing those who studied it to confront the limits of inference and the dangers of overconfidence. Understanding would eventually come, but only after the discipline itself learned how to question not just the sky, but the methods used to interpret it. The galaxy demanded a different kind of thinking, one that accepted uncertainty as data rather than failure. That shift, subtle and uncomfortable, laid the groundwork for everything that followed. It marked the moment when frustration transformed into resolve, and confusion became the motivation to look beyond appearances and search for deeper structure. This realization quietly changed the direction of astronomy. The breakthrough came not from looking harder at the Milky Way itself, but from looking away from it. After decades of confusion, astronomers began to realize that the structure of our galaxy might be revealed indirectly, through objects that did not belong to the disk at all. Scattered far above and below the Milky Way's luminous plane were strange, ancient groupings of stars known as globular clusters, dense spheres containing hundreds of thousands of stars bound tightly together. Unlike most stars, these clusters were not confined to the flat disk. They formed a vast three-dimensional halo surrounding the galaxy, extending far into space in every direction. These clusters held an important advantage. They were old, stable, and numerous, and crucially, they could be observed in many directions across the sky. By carefully measuring their distances, astronomers could reconstruct the overall geometry of the system they orbited. This required new tools and new thinking. Distance could no longer be guessed from brightness alone. Instead, Astronomers relied on special stars within these clusters whose intrinsic luminosity was well understood. By comparing how bright those stars appeared from Earth to how bright they were known to be, distance could finally be measured with confidence. As the data accumulated, a pattern emerged that was impossible to ignore. The globular clusters were not centered on the Sun. They were not even symmetrically distributed around our local region of space. Instead, they formed a roughly spherical swarm centered on a distant point in the direction of the constellation Sagittarius. Wherever that point lay, it was clearly the true gravitational heart of the galaxy. The Milky Way was not arranged around us. We were arranged around it. This realization carried a profound psychological weight. It marked another step in a long sequence of discoveries that steadily displaced humanity from positions of imagined importance. Centuries earlier, Earth had been removed from the center of the cosmos. Later, the Sun itself was revealed to be just one star among countless others. Now, even within our own galaxy, our location was exposed as unremarkable. We were not near the center, not privileged by position, but orbiting far out in the galactic suburbs, tens of thousands of light years from the true core. The authority of this conclusion lay not in philosophy, but in evidence. The globular clusters told the same story regardless of who measured them or where they were observed from. Independent studies converged on the same result. The galactic center was real, distant, and unmistakably not where we lived. This was not an interpretation imposed on the data. It was a structure revealed by it. With this shift came a new way of thinking about the Milky Way. The galaxy was no longer a vague band of light wrapped around the sky. It became a vast system with a defined center, an enormous scale, and a hierarchy governed by gravity. Stars, gas, and dust all moved in response to that central mass, following paths set not by appearance but by invisible forces. The Sun's slow journey around the galaxy was recontextualized as one small part of a much larger rotation, a cosmic year lasting hundreds of millions of Earth years. This discovery also connected astronomy across generations, the same process of demotion that had reshaped humanity. As view of the universe now extended seamlessly into the structure of our own galaxy. Each step followed the same pattern. Assumptions rooted in human perspective were overturned by measurements that revealed deeper order. Each time, the universe grew larger, older, and less centered on human experience. And each time, understanding became richer rather than diminished. Locating the galactic center did more than redefine our address. It provided a reference point that transformed countless other questions. Stellar motions could now be interpreted relative to a true center. The distribution of gas and dust took on new meaning. Spiral structure, rotation curves. And the long-term evolution of the galaxy could be studied with a clarity that had previously been impossible. The Milky Way became a physical object, governed by laws, not a decorative backdrop. There was also an emotional reckoning embedded in this shift. To accept that we occupy no special place, even within our own galaxy, requires a form of intellectual humility that does not come easily. It asks us to let go of comforting intuitions and accept that meaning does not arise from position. The galaxy does not revolve around us, and never did. Our sense of centrality was a product of limited vision, not cosmic design. Yet this loss was paired with a gain. By identifying the true center of the Milky Way, humanity gained a deeper connection to the structure it inhabits. We became participants in a vast, coherent system rather than isolated observers gazing at an unknowable sky. Our insignificance in position was balanced by significance in understanding. We could trace our motion, our history, and our future within a galaxy whose architecture was finally beginning to come into focus. The discovery also underscored a recurring lesson in science. Progress often comes not from looking harder, but from looking differently. The galactic center revealed itself only when astronomers stopped trying to see it directly and instead followed the evidence wherever it led. Globular clusters, distant and seemingly unrelated, became the key to understanding the largest structure humans had ever attempted to map from within. In recognizing the true center of the Milky Way, humanity completed another chapter in its long journey away from imagined centrality. The pattern was by now familiar, yet no less profound. Each displacement made the universe feel colder and more indifferent, but also more honest. The cosmos was not arranged for our convenience or comprehension. It simply was. And in learning where the heart of our galaxy truly lay, far from our home and hidden from easy view, we took one more step toward seeing reality as it is, rather than as we wish it to be. For a long time, darkness was treated as silence. When astronomers pointed optical telescopes toward the center of the Milky Way, they saw little more than obscuring dust and a confused glow of unresolved stars. The assumption was almost automatic. If nothing could be seen, then nothing particularly dramatic was happening. The galactic center was imagined as crowded and complex, but fundamentally ordinary. That assumption would not survive the arrival of a new way of listening to the universe. Radio astronomy began not with grand cosmic questions, but with an engineering problem. In the early 20th century, unexplained radio noise interfered with communications on Earth. Engineers traced some of this static not to storms or machines, but to the sky itself. The discovery was unexpected and unsettling. Space, which appeared dark and empty to the eye, was emitting signals at wavelengths humans had never evolved to perceive. The universe, it turned out, was not quiet at all. We had simply lacked the senses to hear it. Radio waves offered a revolutionary advantage. Unlike visible light, they could pass through dust almost unhindered. The thick clouds that blinded optical telescopes toward the galactic center became nearly transparent at longer wavelengths. When astronomers finally turned radio receivers toward the heart of the Milky Way, they were not prepared for what they found. Instead of silence, they encountered chaos. The galactic center lit up in radio frequencies, revealing a turbulent environment filled with energetic processes invisible to the eye. This alone would have been startling, but the deeper shock came from pattern recognition. Amid the sprawling radio glow, one source stood out. It was compact, extraordinarily bright, and sharply defined compared to the diffuse emissions around it. While most radio signals from the galactic center were extended and complex, this source was small and intense, as if a single point were shouting over a crowd. It appeared to sit precisely where gravity suggested the galactic center should be. The contrast was striking. Visually, the region looked dark and confused. In radio, it was loud and structured. What had seemed like absence was revealed as activity. What had seemed empty was revealed as dense with energy. This inversion of expectation forced astronomers to confront a humbling truth. The universe had been broadcasting its secrets all along, but humanity had been listening on the wrong channel. As radio surveys improved, the anomaly refused to fade. Higher resolution observations showed that this compact source was not an illusion or an artifact of poor instruments. It remained fixed in position while surrounding structures shifted and evolved. Its brightness fluctuated, but its location did not. Whatever it was, it marked something fundamental. It was not just another energetic region. It was the anchor point of the entire galactic center. This realization carried a sense of revelation rather than gradual understanding. There was no smooth transition from ignorance to clarity. Instead, a single technological leap transformed darkness into noise, confusion into signal. The Milky Way's center went from being imagined as quiet and obscure to being recognized as one of the most energetic regions in the galaxy. The idea that the core was ordinary collapsed almost overnight. The discovery also highlighted the power of technological perspective. The universe itself had not changed. Only our method of observation had. By extending human perception beyond the narrow band of visible light, radio astronomy exposed an entirely different layer of reality. It became clear that what we see is only a thin slice of what exists. The most important phenomena in the cosmos often announce themselves in ways that human senses were never designed to detect. As astronomers mapped the radio emissions in greater detail, the uniqueness of the compact source became increasingly difficult to explain. It was too small to be a cluster of ordinary stars, yet too powerful to be dismissed as background noise. It did not resemble known stellar processes. It behaves differently from supernova remnants and star-forming regions. Each attempt to categorize it using familiar objects failed. What made this especially unsettling was its location. The source appeared to sit at the gravitational center of the Milky Way, the point around which stars and gas orbited. This coincidence was unlikely to be accidental. Nature rarely aligns extremes without reason. The simplest explanation was that this object was not merely present at the center, but was the center in a physical sense. It was the source of the gravity shaping the entire region. The name given to this radio source reflected both caution and curiosity. It was labeled as a point of emission, a marker rather than an explanation. Astronomers described what they observed without committing to what it meant. This restraint was deliberate. History had shown how easy it was to mistake novelty for understanding. Better to acknowledge mystery than to rush toward a conclusion that might later unravel. Still, the implications were impossible to ignore. The galactic center was no longer an abstract coordinate defined by star counts and models. It was a real place, broadcasting energy across the galaxy, announcing itself through radio waves that cut effortlessly through the dust. The Milky Way had a voice, and at its heart, that voice was loud. This shift also reshaped the emotional tone of galactic science. The center of the Milky Way was no longer merely distant. It was active, it was dynamic. It was alive with processes that defied easy explanation. The calm, static picture of the galaxy gave way to one of turbulence and power. The idea that something extreme might lurk at the core moved from speculative to unavoidable. Perhaps most importantly, radio astronomy revealed how fragile human assumptions can be. Darkness had been mistaken for emptiness. Silence had been mistaken for inactivity. The universe had been speaking continuously, but only when technology evolved did its message become audible. This realization planted a deeper question that would haunt astronomers for decades. If the galactic center was this loud in radio waves, what kind of object could produce such intensity while remaining invisible to the eye? The emergence of this compact radio source marked a turning point. It was the first unmistakable sign that the heart of the Milky Way was not merely hidden, but fundamentally different from the rest of the galaxy. Something unusual, powerful, and deeply consequential was there. It did not glow like stars or expand like gas clouds. It simply persisted, concentrated, and intense, demanding attention without explanation. In revealing that the galactic center was anything but quiet, radio astronomy did more than add a new tool to astronomy. It shattered a long-held illusion. The Milky Way was not a serene backdrop dotted with stars. It was a complex, energetic system with a restless core. And for the first time, humanity had begun to hear it clearly. When the compact radio source at the galactic center was first identified, the discovery carried a peculiar tension. It was clearly important, clearly unusual, and clearly connected to the deepest structure of the Milky Way. Yet no one rushed to declare what it was. In a field built on precision and skepticism, certainty is earned slowly, and premature claims can unravel careers. The object existed before language existed for it. And that gap between observation and explanation became a defining feature of its early history. The astronomers who first detected the source understood this risk intimately. They had not set out to uncover something fundamental about the galaxy's core. Their original work focused on nearby structures and star-forming regions. The discovery itself came almost incidentally. The result of pointing newly refined instruments toward a region that had long resisted clear interpretation. What emerged was undeniable, a radio source so compact and intense that it stood apart from everything around it. But recognizing significance is not the same as understanding it. In the competitive world of astronomy, bold claims attract attention, but they also invite scrutiny. To declare that one had found the defining object at the center of the Milky Way without overwhelming evidence would have been reckless. At the time, even the existence of black holes as physical objects was still debated. Suggesting that such an object sat at the heart of our own galaxy would have seemed extraordinary, perhaps even irresponsible. So the discoverers did what careful scientists do. They described what they saw, measured what they could, and resisted the temptation to speculate beyond the data. This restraint created a strange kind of suspense. The object was named, catalogued, and observed repeatedly, yet its nature remained unresolved. Papers referred to it in careful technical language, emphasizing properties rather than interpretations. It was compact. It was bright in radio wavelengths. It appeared fixed at the galactic center. Beyond that, conclusions were deferred. The mystery was not dramatized. It was allowed to persist quietly, accumulating weight rather than headlines. The act of naming the object marked a subtle but important shift. A name does not explain, but it acknowledges existence. By giving the source a designation, astronomers claimed it as a subject worthy of sustained attention. The name itself was deliberately modest, a marker within a larger complex of radio emissions in the direction of Sagittarius. The added symbol, a small star-like notation, conveyed excitement without explanation. It signaled that this was something special, something energized, without committing to what that energy meant. Naming also reflects ownership in a deeper sense. Once an object is named, it becomes part of the shared scientific landscape. It can be tracked, debated, refined, and revisited across generations. Sagittarius A** became a focal point not because its nature was understood, but because it demanded to be understood. The name created continuity, allowing observations separated by years or decades to refer back to the same enigmatic source. What stands out in hindsight is how much discipline it took to maintain uncertainty. Science often advances through bold hypotheses, but it survives through restraint. In this case, authority came not from confident declarations, but from careful silence. The astronomers involved earned trust by resisting the urge to oversell their findings. They allowed the evidence to mature, knowing that extraordinary claims require extraordinary support. This approach shaped how the broader community engaged with the object. Instead of polarizing debate, Sagittarius A* became a slow-burning puzzle. Competing ideas emerged, but none dominated prematurely. Some suggested clusters of stars. Others proposed exotic states of matter. A few entertained more radical possibilities. But no explanation was elevated to consensus without being tested against increasingly precise observations. The persistence of mystery played an important psychological role. It kept the field open rather than closing it prematurely. Each new observation added constraints rather than conclusions. The object's compactness, its stability, its brightness, and its location all narrowed the range of plausible explanations, but never quite eliminated uncertainty. This gradual tightening of possibilities created a different kind of suspense, one driven not by drama, but by inevitability. There was also a cultural dimension to this restraint. Astronomy, more than many sciences, deals with phenomena that unfold over timescales far longer than human lives. Patience is not just a virtue, but a necessity. The story of Sagittarius A* unfolded across decades, not years. Instruments improved. Techniques evolved. Entire careers were built around watching the same patch of sky with ever greater clarity. The decision to avoid premature conclusions ensured that the object remained a shared focus rather than a contested claim. Authority without certainty is a delicate balance. Too much caution can stall progress. Too much confidence can mislead. In the case of Sagittarius A*, the balance was maintained by letting the object speak through data rather than interpretation. Each new measurement refined what it could be by eliminating what it could not. Over time, the silence around its nature became as informative as any claim. The name itself took on a symbolic role. It represented a placeholder for ignorance as much as knowledge. To speak of Sagittarius A*, was to acknowledge a gap between observation and understanding. That gap became a productive space, driving technological innovation and theoretical work aimed not at proving a preconceived idea, but at resolving a genuine unknown. In this way, the discovery and naming of Sagittarius A* exemplified scientific integrity at its best. The object was recognized as extraordinary without being mythologized. It was claimed without being explained. Mystery was preserved rather than erased. And in preserving that mystery, astronomers created the conditions for a deeper, more durable understanding to emerge. By the time stronger theories began to coalesce, the groundwork had already been laid. The name was established. The object was accepted as real and central. The community was prepared to follow the evidence wherever it led. Sagittarius A* did not burst onto the scene with a declaration of its true nature. Instead, it entered quietly as a question rather than an answer, demanding patience, humility, and time. The suggestion that the object at the center of the Milky Way might be a black hole did not arrive as a revelation. It arrived as an intrusion. It disrupted comfortable explanations and challenged instincts that even seasoned scientists relied on. At the time, black holes occupied an uneasy space between mathematics and imagination. They existed cleanly in equations, but awkwardly in reality. To propose one at the heart of our own galaxy felt like pushing theory too far, too fast. Part of the resistance was emotional, even if few would have admitted it openly. Black holes carried an unsettling finality. They were objects from which nothing escaped, places where familiar laws seemed to fail, and regions where prediction gave way to abstraction. For astronomers accustomed to stars, gas clouds, and radiation, a black hole felt less like a natural extension of known phenomena and more like a conceptual cliff. Accepting one meant accepting that nature allowed something profoundly extreme to exist. Not just in distant theory, but nearby in cosmic terms. There was also a clash between intuition and implication. The radio source at the galactic center was compact, yes, and massive. Perhaps, but black holes implied densities and gravitational forces that bordered on the absurd. The idea that millions of solar masses could be compressed into a region smaller than our solar system strained physical imagination. Intuition rebelled against it. Surely something else, something more familiar, could explain the observations without invoking an object so exotic. Respected scientists proposed alternatives, and these proposals were not frivolous. One possibility was a dense cluster of stars packed so tightly together that they appeared as a single point source. Another suggested a cloud of hot gas confined by extreme pressure. Some entertained the idea of exotic forms of matter not yet understood. Each hypothesis attempted to preserve continuity with known physics, to explain the data without invoking a phenomenon that many still regarded as theoretical excess. This skepticism was not stubbornness, it was discipline. Black holes, despite their mathematical legitimacy, had a troubled history. For decades after their prediction, even Einstein doubted they could form in nature. The singularities implied by the equations seemed like signs that the theory itself was breaking down rather than describing something real. To leap from cautious observation to black hole declaration would have ignored this legacy of doubt. Social proof also played a role. Science advances through consensus built on evidence, not individual conviction. At the time, there were few confirmed black holes of any kind, and none with the overwhelming certainty later generations would take for granted. To claim that the Milky Way's center contained a supermassive black hole would have placed its proponents far ahead of the prevailing consensus. In a community that values replication and verification, that position carried risk. The cognitive dissonance was sharpened by scale. Black holes were most commonly discussed in the context of collapsed stars, objects a few times more massive than the Sun. The object at the galactic center, if it were a black hole, would dwarf those examples by millions of times. The leap from stellar collapse to supermassive dominance required mechanisms that were poorly understood or entirely unknown. How could something so enormous form? How could it remain stable? These unanswered questions made the hypothesis feel premature. There was also the problem of visibility. Black holes emit no light of their own. They announce themselves only through their effects on surrounding matter. For many astronomers, this indirectness felt unsatisfying. Science prefers objects that can be seen, measured, and characterized directly. To accept a black hole required trusting inference over observation, gravity over light, absence over presence. That inversion was philosophically uncomfortable. Yet the alternative explanations began to strain under scrutiny. Dense clusters of stars would not remain stable over cosmic timescales. Gravitational interactions would cause them to collapse or disperse. Clouds of gas hot enough to produce the observed emissions could not be confined without collapsing inward. Exotic matter proposals lacked independent evidence and predictive power. One by one, the options that preserved intuition began to fail. This created a growing tension within the scientific community. The black hole hypothesis was unsettling, but it was also resilient. It explained compactness, mass, and stability with a single framework rooted in established theory. The resistance to it became less about flaws in the idea and more about discomfort with its implications. Accepting it would mean acknowledging that the universe was capable of producing objects far stranger than everyday experience suggested. The debate revealed a deeper conflict between how science feels and how it functions. Intuition is shaped by environments humans evolved in, environments where gravity is weak and space-time feels rigid. Black holes exist far outside that regime. They demand a surrender of intuition in favor of mathematics and evidence. This surrender does not come easily, even to experts. As evidence accumulated, skepticism shifted in tone. It became quieter, more focused on testing limits rather than rejecting possibilities. Scientists asked not whether the object could be a black hole, but whether any alternative could survive increasingly precise observations. This was a subtle but important change. The hypothesis moved from being radical to being provisional, from being inappropriate to being unavoidable. Still, consensus did not form overnight. The weight of the claim demanded patience. Careers had been built on caution, and reputations depended on rigor. The scientific community moved deliberately, aware that declaring a black hole at the center of the Milky Way would reshape textbooks and understanding alike. The fear was not of being wrong in isolation, but of being wrong publicly about something so fundamental. In this prolonged hesitation, science revealed one of its strengths. It does not reward the boldest idea, but the most durable one. The black hole hypothesis endured not because it was dramatic, but because it withstood challenge. Each new measurement tightened constraints. Each failed alternative strengthened the case. Gradually, what once felt radical began to feel inevitable. The discomfort never fully vanished. Even today, black holes provoke unease. But the early resistance to the idea was not a flaw in science. It was evidence of its self-correcting nature. By demanding extraordinary support for extraordinary claims, the community ensured that when acceptance finally came, it would be grounded not in fascination, but in proof. Long before anyone spoke seriously about black holes as physical objects, the equations already knew they existed. In 1915, when general relativity replaced Newton's gravity with a radically different description of space and time, it quietly opened a door that many physicists would spend decades trying not to walk through. Gravity was no longer a force acting across distance. It became geometry itself, the bending of space-time by mass and energy. And hidden within that geometry was a consequence that could not be wished away. When the equations were first solved for simple cases, they revealed something deeply unsettling. For a sufficiently compact mass, space-time did not merely curve gently as it does around planets and stars. It folded in on itself. There appeared a boundary where escape ceased to be possible, a surface beyond which all paths led inward. At the center of this structure, the mathematics predicted a point of infinite density and infinite curvature. The implications were extreme enough that many assumed the equations had been pushed beyond their proper limits. This reaction was understandable. Infinite quantities rarely signal physical reality. In most areas of physics, they indicate that a theory has broken down and needs revision. Even Einstein himself doubted that nature would allow such objects to form. Surely, it seemed, some unknown process would intervene before matter could collapse so completely. The equations might permit black holes. But intuition insisted that the universe would not. For decades, that intuition held sway. Black holes were treated as mathematical curiosities rather than astrophysical entities. They appeared in papers as thought experiments, not destinations for telescopes. Yet the mathematics refused to soften. As physicists explored the implications of general relativity more deeply, they found that the conditions leading to black holes were not exotic at all. They were the natural endpoint of gravitational collapse once known sources of pressure were exhausted. The shift came gradually, through a series of proofs that stripped away escape routes. Physicists demonstrated that if a sufficiently massive star ran out of nuclear fuel, no known force could halt its collapse. Not radiation pressure, not particle interactions, not rotation. Collapse was not a possibility, but an outcome. The formation of an event horizon became unavoidable. Not because anyone desired it, but because the equations left no alternative. This was a turning point. Black holes were no longer optional features of the theory. They were consequences. You did not have to believe in them. You only had to accept general relativity and follow its logic honestly. Once that step was taken, the existence of black holes followed with the same inevitability as planetary orbits follow from Newton's laws. What made this especially unsettling was the simplicity of the result. Black holes were not complicated objects requiring detailed descriptions. According to the theory, they were defined by only a few properties: mass, spin, and charge. Everything else vanished behind the event horizon. Complexity collapsed into minimalism. The universe, it seemed, allowed regions where information was stripped away, leaving behind something both mathematically clean and physically terrifying. As these ideas matured, resistance shifted from denial to discomfort. Physicists no longer argued that black holes were impossible. Instead, they hoped they were rare, hidden, or irrelevant. But the same mathematics that predicted their formation also predicted their stability. Once formed, a black hole could persist indefinitely, quietly shaping its surroundings through gravity alone. When astronomers began to encounter objects that required enormous mass packed into small volumes, general relativity loomed in the background like a silent judge. Alternative explanations could be proposed, but they had to obey the same equations. Again and again, those alternatives failed not because they were poorly imagined, but because they could not survive mathematical scrutiny. Gravity does not negotiate. It obeys rules, whether those rules feel comfortable or not. This was where disbelief gave way to inevitability. The theory did not argue. It demonstrated. Faced with precise observations and a framework that had already passed every experimental test thrown at it, scientists were forced into a kind of intellectual surrender. To reject black holes now would mean rejecting general relativity itself, a theory that had explained phenomena ranging from the orbit of Mercury to the bending of light by the sun. The fear that accompanied this shift was abstract but real. Black holes implied regions of space-time where prediction failed, where known physics ended. They hinted at a deeper layer of reality, still beyond reach. Accepting them meant accepting ignorance at the heart of understanding, admitting that even the best theories could describe boundaries they could not cross. Yet that acceptance was also a mark of scientific maturity. Science does not require comfort, it requires consistency. Once general relativity was accepted as a description of gravity, black holes ceased to be speculative monsters and became necessary features of the universe. Their existence was not a matter of belief, but of logic carried to its conclusion. By the time astronomers seriously considered the object at the center of the Milky Way, the theoretical ground had shifted. The question was no longer whether black holes could exist, it was whether nature had chosen to create one there. And with each calculation, each proof, each failed alternative, the answer became harder to avoid. The equations had spoken long ago. Humanity was only just catching up. To understand what a black hole is, intuition must be set aside almost immediately. The universe does not behave near these objects the way everyday experience suggests it should. Concepts that feel solid, like space, time, direction, and even cause and effect, begin to blur. A black hole is not simply a very heavy object. It is a region where gravity has altered the structure of reality itself. In everyday life, space feels like an empty stage, and time feels like a steady flow, independent of what happens within them. General relativity overturned that picture. Space and time are woven together into a single fabric called spacetime, and that fabric is flexible. Mass and energy bend it. What we experience as gravity is not a pull, but motion along curved spacetime. Objects follow the paths laid out by that curvature, just as water follows the shape of a valley. Under ordinary conditions, this curvature is gentle. Near Earth or the Sun, spacetime is only slightly warped. Enough to guide orbits and falling objects, but not enough to feel strange. Near a black hole, the curvature becomes extreme. Imagine stretching a rubber sheet and placing a heavy ball at its center. The sheet dips, and smaller objects roll inward. Now imagine the sheet thinning, steepening. It's eventually folding so sharply that everything sliding toward the center can no longer climb back out. That folding point marks the event horizon. The event horizon is not a physical surface. There is nothing solid there, nothing to collide with. It is a boundary defined by motion and time. Outside it, paths through spacetime still allow escape. Inside it, all possible futures lead inward. Crossing it is not marked by fire or force. For someone falling freely, nothing special happens at the moment of crossing. The laws of physics in their immediate surroundings feel unchanged. The horror of the event horizon is not felt locally. It is encoded in destiny. From far away, the story looks very different. As an object approaches the event horizon, its motion appears to slow. Light climbing out of the deep gravitational well loses energy, stretching to redder wavelengths. Time itself runs slower in stronger gravity, and near a black hole, this effect becomes extreme. To a distant observer, the falling object never quite crosses the horizon. It fades, reddens, and seems to freeze in place, suspended forever at the edge. For the falling observer, time behaves normally at first. Seconds tick by as expected. But the geometry of spacetime has turned inward. The direction that once meant down now points toward the future. Inside the event horizon, moving forward in time means moving closer to the center. Escape would require moving backward in time, which is as impossible as undoing yesterday. The singularity is not a place to travel toward. It is a moment to arrive at. This is where fear and fascination intertwine. A black hole does not hunt or pull in objects maliciously. From far away, it behaves like any other mass. Planets could orbit a black hole peacefully if they kept their distance. Danger arises only when something ventures too close, where spacetime tilts so steeply that return becomes impossible. As the fall continues, tidal forces emerge. Gravity is stronger closer to the center than farther away. For a human body, this difference matters. Feet are pulled more strongly than the head, stretching the body lengthwise while compressing it sideways. This process, grimly nicknamed spaghettification, grows more severe the deeper one falls. For supermassive black holes, this stretching becomes deadly only well after crossing the event horizon. For smaller ones, it happens sooner. Either way, the end is inevitable. Time distortion deepens as well. Near the center, space-time curvature grows without bound. The equations predict a singularity, a region where density and curvature become infinite and known physics fails. Whether such infinities truly exist or signal the need for a deeper theory remains unknown. What is certain is that nothing inside the horizon avoids this fate. The future ends there. What makes black holes so unsettling is that none of this relies on violence or drama at the boundary. The transition is smooth, quiet, and final. There is no warning built into sensation. Reality simply narrows until only one outcome remains. The terror lies not in pain, but in inevitability. Yet black holes are also astonishingly elegant. Despite their complexity, they are described by remarkably few numbers. Once formed, all the details of what fell in are erased from the outside universe. Only mass, spin, and charge remain visible. Information appears lost, a puzzle that continues to trouble physicists. The universe allows objects that simplify themselves by consuming complexity. To imagine falling into a black hole is to imagine a universe that does not care about human scale or intuition. Space becomes time. Direction becomes destiny. The familiar rules dissolve not with chaos, but with precision. Black holes reveal that reality is deeper, stranger, and more unforgiving than everyday experience suggests. They are not monsters lurking in space, but consequences of gravity carried to its logical extreme. In them, the universe shows what happens when structure, patience, and inevitability outweigh comfort. When direct observation failed, astronomers turned to motion. If the object at the center of the Milky Way could not be seen, then its gravity could still be traced through its effects. Stars, unlike light, cannot hide their paths. They move according to the mass that governs them, and by watching those movements carefully enough, the invisible can be weighed, measured, and constrained. This approach required a different mindset. Instead of snapshots, astronomers needed patience. Stellar orbits near the galactic center unfold over years and decades, not nights. At first, the stars appeared almost frozen in place, barely shifting against the crowded background. But subtle changes accumulated. Tiny arcs became detectable. The sky, once static, began to move. The challenge was immense. The region around the galactic center is one of the most crowded stellar environments in the galaxy. Thousands of stars overlap within a tiny patch of sky, their light blending together. Dust absorbs visible light, forcing observations into infrared wavelengths. Earth's atmosphere distorts incoming starlight, smearing positions and blurring detail. Every obstacle conspired to make precise measurement nearly impossible. Overcoming these limits required technological innovation and unwavering commitment. Infrared detectors grew more sensitive. Calibration improved. Year after year, teams returned to the same stars, measuring their positions with painstaking care, building a record not of brightness, but of motion. This was astronomy as detective work. Each observation was a clue. A slight shift in position hinted at velocity. Curvature in a path suggested acceleration. Patterns emerged slowly, almost reluctantly, but once they did, they were unmistakable. Some stars were moving far faster than any ordinary stellar population. Their paths bent sharply, looping around an unseen point with astonishing speed. The payoff for this patience was extraordinary. By mapping these orbits, astronomers could apply the same laws that govern planets around the Sun. From the size and shape of an orbit, mass could be inferred. The tighter the orbit and the faster the motion, the greater the central mass must be. In the case of the galactic center, the numbers quickly became staggering. Stars were found to swing around the invisible center at thousands of kilometers per second. Their orbits were compact, elongated, and precise, all converging on the same focal point. This was not a diffuse region of gravity. It was concentrated, sharp, and dominant. Whatever lay there possessed millions of times the mass of the Sun, confined to a region no larger than the solar system. What made this evidence so compelling was its consistency. Each star acted as an independent probe. No single orbit could be dismissed as an anomaly or measurement error. The central mass was real, enormous, and compact beyond any conventional explanation. This method carried a powerful psychological weight. It did not rely on exotic assumptions or speculative physics. It rested on centuries-old principles tested countless times closer to home. Gravity behaved as expected. Orbits followed predictable laws. The only extraordinary element was the mass required to produce what was observed. Trust grew not from spectacle, but from repetition. Year after year, predictions made from earlier measurements were confirmed by later ones. Stars appeared where the equations said they would. Deviations were small, understandable, and correctable. The system behaved like a clockwork governed by a single, dominant gravitational source. The delayed payoff amplified the impact. For years, the data remained suggestive but incomplete. Orbits had not yet closed. Paths were partial. Conclusions were provisional. Then, as enough time passed, the arcs completed themselves. Stars returned to positions they had occupied years earlier, completing full revolutions around the unseen center. The evidence locked into place. There was something deeply reassuring about this process. It demonstrated that truth could emerge without drama, through persistence rather than revelation. No single observation overturned doubt. Instead, doubt eroded gradually, worn down by precision and time. The invisible object did not need to announce itself. Its gravity spoke continuously, and astronomers learned to listen. The emotional tone of this work was shaped by discipline. These observations were not glamorous. They demanded consistency, calibration, and restraint. Careers unfolded alongside orbits. Some astronomers spent decades tracking the same stars, trusting that the accumulation of small measurements would eventually outweigh uncertainty. That trust was rewarded. As the orbits sharpened, alternative explanations collapsed. A cluster of stars dense enough to produce such gravity would not remain stable. It would disperse or merge on timescales far shorter than the age of the galaxy. Clouds of gas could not account for the precise, repeatable motions observed. Each orbit narrowed the range of possibilities until only one remained. The detective story reached its climax, not with a surprise, but with confirmation. The invisible center was exactly where the radio source lay. The mass inferred from stellar motions matched what theory demanded. The unseen object was not a vague region or distributed structure. It was a single dominant presence anchoring the galaxy's core. This approach also reshaped how astronomers thought about evidence. Seeing was no longer the gold standard. Motion became proof. The universe could be weighed without being illuminated. Gravity became a lens, revealing objects that light could not. This shift opened new ways of studying the cosmos, extending far beyond the galactic center. Perhaps the most striking aspect of this achievement was its quietness. No explosion marked the conclusion. No sudden image resolved the mystery. Instead, confidence emerged gradually, solidifying as predictions continued to succeed. The invisible object earned its reality through obedience to law, not through appearance. In watching stars orbit nothing, astronomers demonstrated a rare kind of faith, not belief without evidence, but confidence that evidence would accumulate if patience were maintained. That patience transformed absence into presence. It turned motion into mass. And it provided the most compelling proof yet that something extraordinary sat at the heart of the Milky Way. Unseen, but undeniable. Among all the stars traced near the galactic center, one emerged as decisive. It did not merely suggest an answer. It delivered one. This star, known as S2, transformed decades of careful inference into certainty and turned a lingering hypothesis into established reality. S2 is not remarkable at first glance. It shines brightly, blue-white, and young. One of many massive stars crowded into the central region of the Milky Way. What set it apart was not its appearance, but its path. Unlike most stars, which drift slowly across the sky, S2 moved with urgency. Year by year, its position changed noticeably. Month by month, its motion curved, accelerated, and bent around a point where nothing visible existed. Astronomers quickly realized that S2 was not wandering randomly. It was orbiting something. And it was doing so on a trajectory unlike anything seen elsewhere in the galaxy. Its orbit was highly elongated, carrying it far from the center and then plunging it inward again at tremendous speed. This shape alone hinted at a powerful gravitational source, but the full implications would take time to unfold. The patience required to follow S2 was immense. A single orbit takes about 16 years. To understand its motion fully, astronomers needed to watch it complete an entire revolution, from one close approach to the next. That meant waiting. Instruments had to remain calibrated across decades. Teams had to maintain continuity as students became researchers and researchers became mentors. The star would not hurry to accommodate human timelines. As the years passed, S2 traced more and more of its path. The curve sharpened. The acceleration increased as it approached the unseen center. At its closest point, S2 raced through space at thousands of kilometers per second, moving fast enough to reveal effects predicted only by Einstein's theory of relativity. This was no gentle orbit. It was a plunge into one of the strongest gravitational fields accessible to observation. When S2 completed its first full orbit under continuous observation, the result was definitive. The laws governing orbital motion are unforgiving, from the size of the orbit and the speed of the star. The mass of the central object could be calculated precisely. The answer was staggering. Roughly 4 million times the mass of the Sun was packed into a region no larger than the solar system. This measurement carried a finality that earlier evidence lacked. It was not a suggestion or a lower bound. It was a number, and that number left no room for ambiguity. No cluster of ordinary stars could remain stable with such mass concentrated in such a small volume. No cloud of gas could explain the motion. No exotic alternative survived the math. The only object capable of fitting the data was a supermassive black hole. What made this moment extraordinary was not just the result, but the way it arrived. There was no dramatic announcement, no sudden revelation. The conclusion emerged quietly through consistency. Every calculation pointed to the same mass. Every refinement sharpened the same picture. Independent teams using different telescopes and techniques arrived at the same answer. Authority came not from reputation, but from convergence. S2 did more than weigh the unseen object. It confirmed its location. The focus of the orbit lay exactly where the compact radio source had been detected decades earlier. Two lines of investigation, one tracing light and the other tracing motion, intersected at the same point in space. The center of gravity, the source of radio emission, and the focus of stellar orbits were one and the same. This convergence marked the resolution of uncertainty. For years, astronomers had accumulated hints and constraints. S2 delivered closure. The object at the heart of the Milky Way was not merely massive, it was compact beyond conventional explanation. It was stable over time. It exerted gravity exactly as predicted by general relativity. The case was no longer persuasive. It was complete. The emotional impact within the scientific community was profound. Decades of caution had paid off. The restraint that once delayed bold claims now gave weight to the conclusion. When astronomers finally said that a supermassive black hole existed at the center of the Milky Way, they did so with confidence born of patience rather than enthusiasm. S2's orbit also carried symbolic power. It represented a full arc of inquiry, from speculation to proof. Early doubts about black holes had yielded to mathematical inevitability. Indirect observations had matured into precise measurements. The star itself became a messenger, carrying information from a region that could not speak directly. Beyond confirming the black hole's existence, S2 opened a new chapter. Its extreme motion provided a testing ground for fundamental physics. As it swept through its closest approach, its light shifted in frequency. Its orbit deviated slightly from Newtonian predictions, and space-time itself revealed subtle curvature effects. The black hole was no longer just an object to be inferred. It became a laboratory. This scientific triumph was shared, not owned. Multiple teams contributed to the long campaign, each building on the work of others. The success illustrated how science advances not through isolated breakthroughs, but through sustained collaboration and trust in process. No single observation would have sufficed. Only time could deliver the answer. The resolution brought a sense of closure, but not a finality. The black hole was confirmed, but its deeper nature remained mysterious. The event horizon still hid whatever lay beyond. The singularity remained a mathematical frontier. Yet something fundamental had changed. The question was no longer whether the black hole existed, but how it shaped the galaxy around it. S2's orbit ended an era of doubt and began an era of exploration. The invisible center of the Milky Way had been weighed, located, and confirmed. A star had traced the outline of something that could not be seen, and in doing so, had transformed an abstract idea into a concrete feature of our cosmic home. The triumph lay not only in the answer, but in the method. A demonstration that even the darkest places in the universe can be understood, if one is willing to wait long enough and measure carefully enough. Once the existence of the black hole at the center of the Milky Way was no longer in doubt, its role quietly shifted. It was no longer just an object to be confirmed. It became a place to test reality itself. Few environments in the universe offer gravity strong enough, motion fast enough, and stability long enough to probe the limits of fundamental physics. Sagittarius A* does all three, turning the galactic center into a natural laboratory unlike anything humans could build. Einstein's general theory of relativity had passed every test thrown at it for over a century. But most of those tests occurred in relatively gentle conditions. The orbit of Mercury, the bending of light by the sun, and time dilation measured by satellites all confirmed the theory in weak gravitational fields. Near a supermassive black hole, gravity becomes far stronger, space-time curvature far steeper, and relativistic effects far more pronounced. If the theory were ever going to fail, this was where cracks would appear. The first major test came from light itself, as stars like S2 swept close to Sagittarius A*. Their light had to climb out of an intense gravitational well before reaching Earth. General relativity predicts that this climb costs energy. The light's wavelength should stretch, shifting toward the red end of the spectrum in a phenomenon known as gravitational redshift. This effect had been measured before in laboratories and within the solar system, but never in such an extreme environment. When astronomers measured the spectrum of S2 during its closest approach, the result was precise and unsettlingly clean. The redshift matched Einstein's predictions almost exactly. There was no excess, no deficit, no unexplained deviation. The black hole was not just massive, it was warping spacetime in precisely the way the theory demanded. Gravity behaved not as intuition might suggest, but as mathematics insisted. This was more than confirmation. It was validation under pressure. The stronger the field, the greater the chance of failure. Yet the theory held. The equations that once seemed abstract proved capable of describing reality, even at the edge of the unimaginable. Another test unfolded more slowly, written not in light, but in motion. In Newtonian gravity, an object orbiting a central mass traces the same ellipse over and over, returning to the same closest point each cycle. General relativity predicts something subtly different. The orbit itself should rotate over time, causing the point of closest approach to shift. This effect, known as orbital precession, had been observed for Mercury, but only as a tiny correction. Near Sagittarius A*, it would be far larger. Tracking this required patience bordering on obsession. Astronomers had to follow stars through complete orbits lasting decades, measuring minute changes in orientation with extraordinary precision. When the data finally accumulated, the predicted precession appeared. The orbit of S2 did not close neatly. It rotated, forming a slow rosette pattern around the black hole. Once again, the amount of precession matched the theory. What made these tests remarkable was not just their success, but their independence. Light and motion are different messengers. They probe gravity in different ways, yet both told the same story. Space-time near Sagittarius A* behaves exactly as general relativity predicts. The black hole did not merely exist. It obeyed the deepest known laws of gravity. This convergence produced a powerful sense of intellectual awe. A theory developed on paper, guided by thought experiments and mathematics, was accurately describing a region of space tens of thousands of light-years away, where gravity twists reality into unfamiliar shapes. The human mind, through abstraction, had anticipated phenomena far beyond everyday experience and found them waiting. These tests also mattered far beyond astronomy. General relativity underpins modern cosmology, GPS technology, and our understanding of the universe's origin and fate. Confidence in the theory depends not on belief, but on survival under stress. Each successful test near Sagittarius A* reinforced that confidence. The universe, even in its most extreme environments, still plays by consistent rules. At the same time, the black hole exposed the theory's limits. At the event horizon and beyond, general relativity predicts singularities. Places where density and curvature become infinite and equations lose meaning. Testing gravity near Sagittarius A* sharpened this tension. The theory works extraordinarily well, right up to the boundary where it predicts its own breakdown. This duality, precision alongside incompleteness, is part of what makes the black hole such a powerful probe. There is a subtle emotional shift that accompanies this realization. The success of these tests inspires trust, but also humility. Nature is not obligated to align with human ideas, yet here it does, with uncanny fidelity. At the same time, it reminds us that understanding is provisional. The same equations that describe stellar orbits flawlessly also point toward mysteries they cannot resolve. Sagittarius A*, therefore, occupies a unique position. It is both confirmation and challenge. It validates one of the greatest achievements in physics, while highlighting the frontier where new understanding must emerge. It shows that reality can be predicted with astonishing accuracy, but only up to a point. This is why the black hole's role as a testing ground matters. It transforms abstract theory into lived reality. It shows that mathematics is not merely a language for describing what we see, but a tool for revealing what we cannot. The motions of stars and the shifting of light become experiments conducted by the universe itself, repeating over and over, waiting for careful observers. In this sense, Sagittarius A* is not just an object at the center of the Milky Way. It is a mirror held up to human understanding. Each successful test reflects our capacity to grasp reality at scales far removed from intuition. Each unresolved question reflects how much remains unknown. The triumph lies not in proving Einstein right once again, but in demonstrating that the universe is intelligible even in its most extreme forms. Gravity near a black hole is not chaos. It is structure taken to its limit. And in measuring that structure with precision and patience, humanity has shown that truth can be tested not just in laboratories, but across the vast, silent reaches of space, for an object capable of unimaginable violence. The black hole at the center of the Milky Way is remarkably quiet. It does not blaze across the cosmos. It does not flood its surroundings with lethal radiation. Most of the time, it barely announces its presence at all. This calm is not what astronomers expected, and it is not typical of black holes of similar size elsewhere in the universe. In many galaxies, supermassive black holes are anything but subtle. When large amounts of gas fall toward them, they ignite. Matter spiraling inward heats to extreme temperatures, releasing torrents of energy that can outshine entire galaxies. These active galactic nuclei dominate their environments, carving vast cavities in surrounding gas, launching jets that stretch for thousands of light years, and bathing nearby regions in intense X-rays and gamma rays. They are engines of destruction and creation, shaping the evolution of galaxies on the grandest scales. Sagittarius A* does almost none of this today. It feeds sparingly, consuming only a trickle of material. Its accretion flow is thin, chaotic, and inefficient at producing radiation. Compared to the blazing cores of distant galaxies, it is practically starving. This contrast is striking. The same laws of physics apply. The same mass anchors the system, yet the outcome could not be more different. The reason lies not in the black hole itself, but in its environment. Activity depends on fuel. Black holes shine only when they are fed, and Sagittarius A* lives in a region where food is scarce and difficult to capture. The gas near the galactic center is hot, turbulent, and fast-moving. Instead of falling inward, much of it whips past the black hole or is blown away by stellar winds. Angular momentum acts as a barrier, preventing material from surrendering itself easily to gravity's pull. This inefficiency keeps the black hole quiet, and that quiet has consequences. A more active Sagittarius A* would transform the inner Milky Way into a hostile place. Powerful radiation would strip atmospheres from nearby planets. High-energy particles would disrupt chemistry and damage emerging life. Entire regions of the galaxy could be sterilized, not by explosions, but by persistent exposure to energetic light. The calm we observe today is therefore a form of cosmic luck. The Milky Way is not unique in hosting a supermassive black hole, but it is fortunate in hosting one that is currently dormant. Our galaxy is old, and evidence suggests that Sagittarius A* was more active in the past. Vast structures of energized gas above and below the galactic plane hint at ancient outbursts millions of years ago, episodes when the black hole briefly flared to life. Those events ended, and the galaxy settled into a quieter state. This timing matters. Complex life requires stability over long periods. It needs relatively calm radiation environments, predictable stellar behavior, and time for biological processes to unfold. Our position far from the galactic center already provides distance from danger. The current quiescence of Sagittarius A* adds another layer of protection. Together, these conditions create a narrow window in which life can persist. The contrast with active galaxies sharpens this perspective. In those systems, central black holes regulate star formation, heating gas so strongly that new stars struggle to form. Entire galaxies can be quenched by their own cores. The Milky Way, by comparison, remains fertile. Stars continue to form. Planetary systems emerge. The galaxy evolves gently rather than violently. This does not mean Sagittarius A* is harmless. It remains immensely powerful, capable of awakening if conditions change. A large influx of gas or the disruption of a star could trigger a temporary flare, but the key point is scale and duration. Short bursts are survivable at great distances. Continuous activity is not. The black hole's current restraint allows the Milky Way to remain a hospitable home. There is a quiet emotional shift that comes with recognizing this. The same object that once inspired fear becomes, indirectly, a protector, not through intention or design, but through circumstance. The universe did not arrange itself for our benefit, yet the conditions that exist happen to align with our survival. This realization invites a form of existential gratitude, not toward the black hole itself, but toward the fragile balance that governs cosmic systems. The calm of Sagittarius A* also reminds us that extremes are contextual. Black holes are not inherently destructive. They are amplifiers. Given enough material, they become luminous and transformative. Deprived of it, they fade into the background, exerting influence quietly through gravity alone. Their behavior reflects their surroundings as much as their nature. Understanding this quiet phase deepens our appreciation of how galaxies evolve. Activity is not constant, comes in cycles, shaped by mergers, gas flows, and chance encounters. The Milky Way happens to be in a calm chapter, and we happen to exist within it. That coincidence carries weight. There is no guarantee this tranquility will last forever. Over cosmic timescales, conditions will change. Gas clouds may drift inward. Orbits will evolve. The black hole may awaken again. But cosmic timescales are long, and life operates on shorter ones. For now, the silence at the galaxy's center is a gift of time. This perspective reframes our relationship with the cosmos. Instead of viewing the universe as actively hostile, it becomes selectively dangerous, shaped by balances and transitions. Catastrophe is possible, but not constant. Stability is rare, but real. Life exists not because the universe is gentle, but because gentleness sometimes emerges from complexity. Sagittarius A* embodies this paradox. It is a monster that sleeps, a force of annihilation that currently allows creation to continue. Its quiet is not weakness, but circumstance. And within that circumstance, stars shine steadily, planets endure, and on at least one world. Beings arise who can look toward the galactic center and feel both relief and awe. In recognizing how close the Milky Way may have come to being far less hospitable, gratitude becomes a rational response, not sentimental, not mystical, but grounded in understanding. The calm at the heart of our galaxy is not guaranteed, not permanent, and not common. It is simply what is, and for now, it is enough. Sagittarius A* ultimately resists being reduced to a conclusion. Even after decades of observation, precise measurements, and triumphant confirmation, it remains less an answer than a reminder. It reminds us that understanding does not arrive all at once, that reality does not reveal itself on human schedules, and that some of the most important truths exist far beyond the reach of intuition. The story of the black hole at the center of the Milky Way is, at its core, a story about patience. Generations of astronomers devoted their lives to watching stars move by fractions of an arcsecond, trusting that meaning would emerge if they waited long enough. Many of them never saw the final confirmation themselves. They worked, knowing that the payoff might belong to others. This is a form of humility rarely celebrated, yet essential to how knowledge advances. The universe does not rush to accommodate curiosity. It yields only to persistence. There is humility, too, in how often intuition failed along the way. Darkness was mistaken for emptiness. Silence was mistaken for inactivity. Stability was mistaken for simplicity. Again and again, what felt obvious turned out to be misleading. The Milky Way looked calm, yet its heart held something extreme. Space felt empty, yet it was structured by invisible forces. Time felt absolute, yet it bent and slowed under gravity's influence. Sagittarius A* stands as proof that the universe does not care how reality feels to us. It operates according to deeper rules that must be learned, not assumed. Time itself plays a different role in this story. Human lives are brief. Civilizations are fleeting. Even recorded history is a blink compared to the rhythms of the galaxy. Stars take millions of years to evolve. Orbits near the galactic center unfold over decades. Black holes grow over billions of years. Understanding such systems requires stretching thought across scales that are emotionally difficult to hold. Sagittarius A asterisk forces that stretch. It asks us to think in years longer than lifetimes and distances larger than comprehension. In doing so, it reframes identity. Humanity is not central, not privileged by position, and not especially durable. Our planet circles an ordinary star in the outer reaches of an ordinary galaxy, itself one among hundreds of billions. And yet, from this unremarkable vantage point, beings have emerged who can infer the presence of an invisible object tens of thousands of light years away. Weigh it, test the laws of gravity around it, and understand its role in shaping an entire galaxy. Insignificance of position does not imply insignificance of mind. This is one of the quiet revelations embedded in the story. Meaning does not come from being central. It comes from being capable of understanding. The Milky Way does not revolve around us, but it can be known by us, at least in part. That ability is fragile, contingent, and temporary, but it is real. Sagittarius A asterisk exists whether or not it is observed, yet its story exists only because curiosity persisted long enough to uncover it. There is also a lesson in restraint. Even now, after confirmation, much remains hidden. The event horizon marks a boundary not just in space, but in knowledge. Beyond it, prediction ends. The singularity, if it exists, lies outside current understanding. No telescope can see it. No equation can fully describe it. Sagittarius A teaches that knowledge has edges, and that encountering those edges is not failure. It is part of honest inquiry. This absence of closure is not a weakness of science, but one of its defining features. Each answer sharpens new questions. Each confirmation exposes deeper uncertainty. The black hole is known as a mass, a location, a gravitational influence. It is unknown as an interior, a final state, a reconciliation between gravity and quantum reality. The universe remains larger than any framework used to describe it. Emotionally, this can feel unsettling. Humans prefer narratives that resolve, mysteries that conclude. Sagittarius A asterisk refuses that comfort. It offers awe without completion. It invites contemplation without finality. In that sense, it resembles the night sky itself. The more we learn, the more vast it becomes. Yet there is something grounding in this realization. The limits of knowledge do not diminish what has been learned. They contextualize it. They remind us that understanding is not possession, but relationship. We engage with reality through models, measurements, and metaphors, always aware that they are approximations. Sagittarius A asterisk stands as a boundary object, marking how far those approximations can go. It also reframes fear. Black holes are often portrayed as cosmic threats, devourers lurking in space. The truth is quieter and more nuanced. Sagittarius A asterisk is not hunting. It is not advancing. It is simply there, following the same laws as everything else. Its danger is conditional, its influence structured. Understanding replaces terror with respect, replacing imagined menace with measured reality. In this way, the black hole becomes a mirror. It reflects human tendencies to anthropomorphize, to exaggerate, to project emotion onto the unknown. It also reflects our capacity to correct those instincts through evidence and patience. The transformation from fear to understanding is not just scientific, it is psychological. Perhaps the most enduring impact of Sagittarius A asterisk is the perspective it enforces. It reveals how much of reality unfolds without regard for observation. The galaxy rotated, stars orbited, and space-time curved long before anyone noticed. Human awareness is recent, partial, and fleeting. And yet, within that brief window, it has managed to glimpse structures that operate on scales vastly larger than itself. That realization invites a different kind of awe. Not the awe of spectacle, but the awe of coherence. The same laws apply everywhere. Gravity bends space-time near Earth and near a black hole. Light shifts in frequency, whether measured in a laboratory or near the center of the galaxy. Reality is consistent across scale, even when intuition fails. Sagittarius A* also serves as a reminder that discovery is often indirect. The most important things are not always those that shine brightest. They are the ones that shape everything else. The black hole cannot be seen, yet it defines the motion of millions of stars. In a broader sense, this reflects how influence often operates quietly, shaping outcomes without announcement. As the story ends, there is no final revelation waiting beyond the horizon. There is only continued observation, refinement, and curiosity. Future instruments will see closer. New theories may reshape understanding. Perhaps one day, the nature of singularities will be resolved, or perhaps new mysteries will take their place. What remains is the aftertaste of scale and patience. The Milky Way is larger, older, and stranger than it appears. The universe contains structures that defy everyday reasoning, yet obey precise laws. And humanity, small and temporary, has learned to listen, measure, and understand enough to glimpse those truths. Sagittarius A* does not offer comfort. It offers perspective. It reminds us that reality is deeper than intuition. That knowledge is earned slowly, and that awe does not require closure to endure. For something defined by consumption, Sagittarius A* eats remarkably little. The popular image of a black hole suggests relentless hunger, a cosmic vacuum cleaner devouring everything nearby. Reality is far less dramatic and far more instructive. At the center of the Milky Way sits an object capable of consuming stars, yet it spends most of its time barely feeding at all. This contrast between expectation and behavior is one of the most revealing aspects of Sagittarius A*, because it exposes how gravity, motion, and structure work together to resist even the strongest pull in nature. Accretion is the process by which black holes grow, but it is not a simple matter of falling straight inward. Almost nothing in the universe approaches a black hole without sideways motion. Gas clouds, stellar winds, and debris all carry angular momentum, a tendency to keep moving sideways rather than plunging directly toward the center. This sideways motion is not a minor detail. It is the primary obstacle that prevents matter from being swallowed easily. As material drifts toward Sagittarius A*, it does not drop straight in. Instead, it begins to orbit. Gravity pulls inward, motion carries it sideways, and the result is a slow spiral rather than a direct fall. Over time, this spiraling material forms an accretion flow, a rotating structure where gas circles the black hole many times before it has any chance of reaching the event horizon. In this sense, most of the struggle is not against gravity, but against motion. For matter to cross the event horizon, it must lose angular momentum. It must somehow shed its sideways motion and spiral inward. This loss is not automatic. It requires friction, collisions, or magnetic interactions that allow energy and angular momentum to be redistributed. Without these processes, matter simply remains in orbit, circling indefinitely without ever being consumed. Around many black holes, these processes are highly efficient. Dense, cool gas settles into thin, bright accretion disks where friction converts gravitational energy into intense radiation. These disks glow brilliantly, making active black holes some of the brightest objects in the universe. Sagittarius A* is nothing like this. Its accretion flow is sparse, hot, and turbulent. Instead of forming a thin, orderly disk, the gas remains puffed up, disorganized, and inefficient at radiating energy. This inefficiency is crucial. In Sagittarius A*, much of the energy released as matter spirals inward does not escape as light. Instead, it heats the gas itself, raising temperatures to millions of degrees. hot gas expands, becomes more resistant to further collapse. Rather than settling inward, much of it is pushed back out, escaping the black hole's grasp before it ever reaches the event horizon. Gravity wins locally, but loses globally. The result is a paradoxical system. The closer matter gets to Sagittarius A*, the harder it becomes to fall in. Heating creates pressure. Pressure resists collapse. The very act of accretion undermines itself. This self-limiting behavior is one of the reasons the black hole remains dim and quiet today. Stellar winds play a major role in this process. Massive stars near the galactic center shed enormous amounts of material in fast-moving winds. This gas provides a steady supply of potential fuel, but it arrives already hot and fast. Much of it simply overshoots the black hole, flying past on curved trajectories before escaping again. Only a small fraction is captured into orbit, and an even smaller fraction makes it all the way inward. Measurements suggest that Sagittarius A* consumes roughly the mass of Earth over thousands of years. On human scales, that sounds immense. On black hole scales, it is starvation. At this rate, the black hole gains mass at a pace so slow it would take longer than the age of the universe to double its size. Compared to actively feeding black holes elsewhere, which can consume the mass of the Sun every year, Sagittarius A* is barely eating crumbs. This inefficiency demystifies the black hole without diminishing its power. Sagittarius A* is not weak. Its gravity is overwhelming, but gravity alone is not enough. Motion matters. Structure matters. The universe is not arranged for matter to fall neatly inward. Even the strongest gravitational trap struggles to overcome the stubbornness of angular momentum. Magnetic fields add another layer of complexity. The gas near Sagittarius A* is ionized, meaning it carries electric charge and interacts strongly with magnetic fields. These fields twist, tangle, and reconnect within the accretion flow, stirring turbulence and transferring energy. Sometimes this process helps gas lose angular momentum and fall inward. Other times, it flings material outward in weak outflows. The result is a chaotic balance rather than a steady intake. What makes this behavior fascinating is how ordinary it is. Nothing about Sagittarius A*'s feeding process requires exotic physics. It is governed by the same principles that keep planets in orbit and storms swirling in Earth's atmosphere. The difference lies in scale, not in kind. Familiar rules applied under extreme conditions produce outcomes that feel counterintuitive but are entirely consistent. This calm inefficiency also explains why the black hole can remain so influential without being destructive. Gravity shapes stellar orbits regardless of how much matter is accreted. Sagittarius A* anchors the galaxy's core, whether it shines or not. Its mass matters far more than its appetite. Even while barely feeding, it defines the motion of millions of stars. There is a quiet lesson in this contrast. Power does not always announce itself through activity. Influence does not require constant action. The black hole's role as a gravitational center is independent of its luminosity. It can be nearly invisible and still dominate its surroundings completely. Understanding this reshapes how black holes are imagined. They are not cosmic vacuums indiscriminately devouring space. They are selective, constrained by physics that resists simplicity. Most matter that approaches Sagittarius A* never reaches the event horizon. It circulates, heats, escapes, and returns to the galaxy. The black hole influences far more material than it ever consumes. This inefficiency also carries a subtle sense of relief. If black holes fed easily, galaxies would look very different. Matter would vanish more readily. Stability would be harder to maintain. The stubbornness of angular momentum and the self-regulating nature of accretion are not accidents. They are features of a universe that balances extremes with resistance. Sagittarius A* stands as a demonstration of this balance. Immensely powerful, yet restrained, capable of growth, yet currently quiet, surrounded by fuel, yet unable to consume most of it. The feeding process that seems inevitable in theory becomes improbable in practice. In watching how little the black hole eats, astronomers learn something essential about how the universe works. Even at the edge of space-time, simple rules apply. Motion resists collapse. Heat resists gravity. Order emerges from tension rather than dominance. Sagittarius A* is not a monster endlessly feeding in the dark. It is a patient center, shaping its environment far more through presence than through consumption. The dimness of Sagittarius A* is not an absence of activity, but the presence of a different kind of physics. At first glance, this seems contradictory. Matter falling into a deep gravitational well should release enormous amounts of energy. In many black holes, it does. They shine because gravity converts motion into heat and heat into light. Sagittarius A* follows the same laws, yet arrives at a radically different outcome. The reason lies in how energy moves, where it goes, and why it rarely escapes. In a radiatively efficient system, accreting gas cools as it spirals inward. Friction between neighboring layers of gas converts orbital energy into heat, and that heat is quickly radiated away as light. Cooling allows the gas to settle into a thin, orderly disk, where each ring transfers angular momentum outward and sinks inward in a controlled way. Brightness is the byproduct of order. Sagittarius A* never reaches this state. Near the galactic center, the gas is extremely thin. Particles collide infrequently, which means they cannot easily share energy or settle into equilibrium. Instead of forming a cool, flat disk, the accretion flow becomes thick, puffed up, and chaotic. Heat builds faster than it can escape. The gas grows hotter and more turbulent the closer it gets to the black hole, until cooling becomes the exception rather than the rule. This is the essence of a radiatively inefficient accretion flow. Energy is generated, but it is not released as light. Instead, it is stored within the gas itself. Temperatures climb to millions or even billions of degrees, but the gas remains optically thin, unable to radiate efficiently. The result is a system that is energetic but dim, active but quiet. Turbulence plays a central role in maintaining this state. Gas in the accretion flow does not move smoothly. It churns, twists, and shears, driven by instabilities that arise naturally in rotating fluids. These motions constantly redistribute energy and angular momentum, but not in a clean, directional way. Instead of steadily feeding the black hole, turbulence traps energy locally, preventing it from being converted into radiation. Magnetic fields intensify this effect. The gas surrounding Sagittarius A* is ionized, meaning its particles carry electric charge and are tightly coupled to magnetic fields. As the gas rotates, these fields are stretched and twisted, storing energy like coiled springs. When the tension becomes too great, the fields reconnect, releasing bursts of energy that further heat the gas. This process is violent on small scales, but inefficient on large ones. Energy is injected back into the flow rather than being radiated away. The irony is that magnetic fields are essential for accretion to occur at all. Without them, angular momentum would be conserved too perfectly, and matter would remain in stable orbits forever. Magnetic turbulence provides the friction needed to move angular momentum outward. But in Sagittarius A*, this same mechanism over-delivers. Instead of gently draining energy into light, it pumps energy into heat and motion, inflating the accretion flow and slowing its inward progress. As the gas heats, it becomes lighter and more buoyant. Rather than sinking inward, much of it rises and escapes in weak outflows. These are not dramatic jets like those seen in active galaxies, but slow leaks that bleed material away before it can be swallowed. In this way, the accretion flow sheds mass as efficiently as it sheds energy, keeping the black hole underfed. What makes this system so compelling is how delicately balanced it is. Small changes in density, temperature, or magnetic structure could push the flow toward a brighter state. Add enough cool gas, and the system could collapse into a thin disk and ignite. Remove too much, and accretion could nearly halt. Sagittarius A* sits in a narrow regime where inefficiency sustains itself. This hidden complexity rewards patience. For years, the black hole's faintness was a puzzle rather than a clue. It seemed to contradict basic expectations. Only by examining the microphysics of hot, magnetized plasmas did the picture begin to make sense. The dimness was not a failure of gravity, but a triumph of competing processes that redirected energy away from light. There is a quiet elegance in this explanation. No exotic particles are required. No new laws need to be invented. The same physics that governs laboratory plasmas and stellar atmospheres scales up to the galactic center, producing behavior that feels counterintuitive only because of the environment's extremity. Complexity emerges not from strangeness, but from interaction. This understanding also deepens respect for the observational achievement. Detecting Sagittarius A* emissions requires extraordinary sensitivity. Astronomers are not seeing a blazing beacon, but faint flickers produced by electrons spiraling in magnetic fields and hot gas emitting weak radiation. Every photon carries information about turbulence, temperature, and structure in a region where direct measurement is impossible. The slow intellectual reward comes from realizing that the black hole's quietness is itself a message. It tells us how matter behaves when pushed to limits without crossing into violence. It shows how systems can regulate themselves, preventing runaway growth through feedback that emerges naturally from physics. There is also a philosophical resonance here. The most extreme object in the galaxy is not loud by default. It does not demand attention. Its complexity is hidden, revealed only through careful analysis and sustained observation. Understanding it requires letting go of simple narratives and embracing layered explanations where multiple forces counterbalance one another. Radiatively inefficient accretion flows challenge the intuition that power must be visible. They demonstrate that energy can circulate without spectacle, shaping outcomes quietly. Sagittarius A* is not dim because nothing is happening. 'Tis dim because too much is happening at once, with energy trapped, recycled, and redirected instead of escaping. This reframes the black hole once again. It is not merely a consumer, but a processor. Matter enters a regime of intense interaction where gravity, heat, turbulence, and magnetism wrestle for dominance. Most of that matter emerges changed, heated, and expelled, carrying the imprint of that encounter back into the galaxy. In the end, the black hole's faint glow becomes a kind of signature. It signals a state of balance between extremes, a regime where growth is slow and influence is subtle. To understand why Sagittarius A* is dim is to understand how complexity can suppress drama, how the universe often prefers stability over excess. The reward for following this trail of reasoning is not a single striking image, but a deeper coherence. The quiet center of the Milky Way is not an anomaly. 'Tis a natural outcome of physics operating at scale. A reminder that even in the presence of overwhelming gravity, the universe finds ways to resist simplicity and preserve balance. The quiet we observe at the center of the Milky Way today is not the whole story. It is a snapshot taken in the present, not a record of the past. When astronomers began to look beyond the immediate surroundings of Sagittarius A*, they found signs that the black hole has not always been so restrained. Imprinted across the galaxy are structures that do not belong to the calm era we inhabit. They are vast, energetic, and impossible to explain without invoking a far more violent chapter in the Milky Way's history. The first clues did not come from the center itself, but from the space above and below the galactic plane. They're extending tens of thousands of light-years into intergalactic space. Astronomers identified enormous lobes of energized gas. These structures were symmetrical, aligned with the galaxy's core, and filled with high-energy particles. They did not resemble the chaotic debris of random events. they looked organized, directional, and purposeful, as if something deep within the Milky Way had once released an immense amount of energy straight out of its heart. What made these structures so unsettling was their scale. They dwarfed anything produced by ordinary stellar processes. Supernova, even in large numbers, could not account for such coherent, colossal formations. Star formation alone lacked the necessary power and focus. The geometry pointed inward, toward the galactic center, and the timescales involved stretched back millions of years. Whatever created them had acted briefly, powerfully, and long ago. This realization revived an old question in a new form. If Sagittarius A* is quiet now, what would it look like when it was not? Black holes do not change their nature, but their behavior depends on what they are given to consume. A sudden influx of gas, the disruption of a star, or the merger with another galaxy could all trigger an active phase. The fossil structures surrounding the Milky Way suggest that such a trigger once occurred. These features behave like cosmic memory. Gas does not forget energy easily. Once heated or accelerated, it can carry that signature for millions of years as it expands and cools. Long after the central engine shuts down, the effects of its activity remain, drifting outward like ripples from a stone dropped into a still pond. The galaxy, in this sense, remembers its own past even when the source has gone silent. Temporal contrast sharpens the mystery. Today, Sagittarius A* emits faint flickers of radiation, barely registering against the cosmic background. In the past, it may have rivaled the brightness of active galactic nuclei seen across the universe. The same object, the same mass, the same laws of physics, but a radically different outcome. This contrast forces a reconsideration of what normal means. Quiet is not permanent. It is a phase. Further evidence appears closer to home. X-ray reflections detected in nearby molecular clouds suggest that intense bursts of radiation once flooded the region around the galactic center. These clouds act like mirrors, scattering high-energy light long after the source has faded. By measuring these echoes, astronomers can reconstruct the brightness of past outbursts, even though the original light is long gone. The picture that emerges is of a black hole that flared dramatically within the last few million years, then settled back into dormancy. The suspense lies not in what happened, but in how easily it could happen again. The fossil records do not point to a single catastrophic event, but two repeated episodes of activity separated by long periods of calm. The Milky Way appears to breathe on cosmic timescales, alternating between quiet stability and energetic release. Sagittarius A* is not broken or special. It is behaving exactly as supermassive black holes are expected to behave when conditions change. This perspective reshapes the present. The calm we experience is not guaranteed. It is contingent. It depends on the availability of gas, the dynamics of stars near the center, and the slow evolution of the galaxy itself. The structures hanging above and below the galactic plane are not relics of an alien past. They are reminders of futures that remain possible. What makes these remnants so powerful psychologically is their silence. They do not announce themselves unless one knows how to look. They occupy vast volumes of space, yet they are faint, revealed only through careful measurement across multiple wavelengths. Like scars, they are visible only in the right light. Once seen, they cannot be unseen. There is also a humbling aspect to this discovery. Human history spans thousands of years. These outbursts occurred millions of years ago, long before humans existed, and their consequences will persist millions of years into the future. The galaxy operates on rhythms that dwarf human concerns. Our present moment, with its quiet black hole and stable environment, is a thin slice through a much longer story. Cosmic memory operates without intention. Sagittarius A* does not remember its past in any conscious sense. Yet the structures it created remain, encoding information about energy, direction, and duration. By reading those structures, astronomers reconstruct events that no one witnessed, turning absence into narrative. This ability to infer history from remnants is one of science's most subtle powers. The existence of these fossils also deepens the meaning of the black hole itself. Sagittarius A* is not just a mass anchoring stellar orbits. It is an engine capable of reshaping the galaxy when conditions align. Its quietness today is not a sign of weakness, but of timing. The same object that now whispers once roared. This realization invites a different kind of awe. Not the awe of immediacy, but of depth. The Milky Way is not static. It carries layers of history written into its structure, each one shaped by forces that operate beyond direct perception. Sagittarius A* sits at the center of that history, not as a constant destroyer, but as a variable influence whose impact depends on context. There is no exact date stamped on these ancient outbursts. The evidence is suggestive rather than definitive, and that uncertainty keeps the mystery alive. Science rarely offers perfect reconstruction. Instead, it offers converging lines of inference that point toward a coherent story without exhausting it. The galaxy's past remains partially obscured, just as its center once was. In this way, the fossil structures serve as a bridge between ignorance and understanding. They hint at what Sagittarius A* can do without fully revealing how often or how violently it has done it. They restore a sense of dynamism to a system that might otherwise appear settled and complete. The calm we observe now is real, but it is not eternal. The Milky Way remembers a different state, one where its center burned brighter and reached farther. That memory lingers in the shape of gas, the glow of distant radiation, and the quiet implication that even the most stable environments are temporary. Sagittarius A* has a past, and in that past lies a reminder that the universe is always capable of changing its tone. When Sagittarius A* was more active, its influence did not announce itself through destruction alone. It reshaped the Milky Way in quieter, more complex ways, altering how gas moved, where stars formed, and how the galaxy evolved as a system. Black holes do not need to tear galaxies apart to leave a lasting imprint. Their power lies in how efficiently they redistribute energy, nudging vast structures onto new paths. Gas is the raw material of galaxies. It collapses to form stars, fuels stellar nurseries, and determines how quickly a galaxy grows and changes. When Sagittarius A* entered an active phase, the energy released by infalling matter did not simply vanish into space. Radiation, winds, and outflows pushed back against surrounding gas, heating it, stirring it, and sometimes ejecting it entirely from the central regions. This feedback altered the balance between collapse and support, changing where and when stars could form. In regions close to the galactic center, intense radiation would have heated molecular clouds, making them less likely to fragment and collapse under their own gravity. Star formation slows when gas is too hot or too turbulent. At the same time, shocks driven by outflows could compress gas farther out, triggering bursts of star formation in more distant regions. The black hole did not act as a simple on-off switch. It acted as a regulator, suppressing growth in some places while encouraging it in others. This cause and effect chain unfolds across scales that are difficult to grasp. A process occurring within a region smaller than the solar system can influence gas clouds thousands of light-years away. Energy released near the event horizon travels outward, carried by radiation and fast-moving particles, coupling the smallest and largest structures in the galaxy. Sagittarius A* becomes a mediator between scales, linking microscopic physics to galactic architecture. Evidence for this influence appears in the distribution of gas near the Milky Way's center. There are cavities where material seems to have been cleared out, alongside dense rings and streams where gas has piled up. These features are not random. They reflect episodes of injection and removal, of pressure applied and released. Over millions of years, such patterns accumulate, shaping the long-term evolution of the galaxy. Star formation histories also bear subtle fingerprints of past activity. Some regions show signs of synchronized bursts, suggesting that a common trigger compressed gas over large areas at roughly the same time. Others show prolonged lulls, periods when conditions were hostile to starbirth. These rhythms are difficult to explain through stellar processes alone. They point to a central influence capable of coordinating change across vast distances. What makes this process remarkable is its restraint. Even during active phases, Sagittarius A* did not destroy the Milky Way. The galaxy remains intact. Its disk stable, its spiral structure persistent. Black hole feedback operates within limits. Governed by the amount of available fuel and the efficiency with which energy couples to surrounding matter. Too little coupling and the black hole's influence remains local. Too much, and the galaxy could be stripped or quenched entirely. The Milky Way appears to have occupied a middle ground. This balance highlights a key insight of modern astrophysics. Black holes and galaxies evolve together, each shaping the other. The growth of the black hole influences star formation, which in turn determines how much gas reaches the center. Feedback creates a loop rather than a one-way process. Sagittarius A* did not simply impose its will on the galaxy. It participated in a dynamic exchange. Systems thinking becomes essential here. Isolating the black hole from its environment misses the point. Its impact cannot be understood without considering gas dynamics, stellar winds, magnetic fields, and the gravitational structure of the galaxy as a whole. Each component responds to the others, creating emergent behavior that no single element controls alone. This interconnectedness challenges simple narratives of cosmic violence. Black holes are often portrayed as destroyers, but their more common role may be as architects of balance. By preventing gas from collapsing too rapidly in the center, they help regulate growth and maintain structure over billions of years. Without this regulation, galaxies could burn through their fuel quickly, leaving behind dim, exhausted systems. The Milky Way's relative longevity may owe something to Sagittarius A*'s intermittent influence. Periods of activity could have cleared excess gas, preventing runaway star formation that would destabilize the disk. Periods of calm allowed gas to cool and settle, sustaining starbirth over long timescales. The galaxy we inhabit is not the product of constant conditions, but of alternating phases shaped in part by its central black hole. Scale escalation deepens the sense of awe. A process that begins with plasma spiraling near an event horizon ripples outward to affect star clusters, spiral arms, and the overall appearance of the galaxy. The sheer range of scales involved, from kilometers to tens of thousands of light years, underscores how deeply interconnected cosmic systems are. The Milky Way is not a collection of independent parts. It is a single organism responding to internal and external pressures. This perspective reframes the black hole's past activity as formative rather than catastrophic. Sagittarius A* did not erase the conditions for life. It helped sculpt them. By influencing where stars formed and how gas circulated, it indirectly shaped the environments in which planets later emerged. The consequences of its activity are subtle, delayed, and diffused across time, but they are real. There is a sobering implication here. Galactic environments are not fixed backdrops. They evolve, influenced by processes that may be dormant for millions of years and then briefly awaken. Stability is an outcome, not a guarantee. The Milky Way's present calm reflects a balance achieved through past upheavals, not an absence of them. Understanding this interplay also reshapes how astronomers interpret other galaxies. When distant galaxies show signs of suppressed or enhanced star formation, black hole feedback is no longer an abstract idea. It becomes a concrete mechanism, one that has operated in our own cosmic home. Sagittarius A** serves as a local example of a universal process. The awe lies not in spectacle, but in consequence. The black hole's influence is written into the structure of the galaxy, into the distribution of stars and gas, into the long arc of its evolution. It demonstrates how immense power can be exercised with restraint, how energy released briefly can shape outcomes for eons. In tracing these cause-and-effect chains, the Milky Way emerges as a system shaped by dialogue rather than domination. Sagittarius A* speaks through energy and gravity. The galaxy responds through motion and structure. Neither acts alone. Together, they form a history written not in explosions, but in patterns that endure. The realization that a black hole can influence a galaxy without destroying it adds nuance to our understanding of cosmic power. It shows that the universe favors regulation over chaos, balance over excess. Sagittarius A* is not merely a threat or a curiosity. It is a participant in the long process that turned gas into stars, stars into systems, and systems into a galaxy capable of sustaining complexity. Seen this way, the black hole's past activity becomes part of a larger story of emergence. The Milky Way is not the victim of its center, nor its master. It is its partner in an intricate dance, one where energy, matter, and time cooperate to produce a structure far more stable and enduring than any single component could achieve on its own. Imagine the Milky Way with its calm center replaced by brilliance. Not a gentle glow, but a sustained, piercing radiance pouring outward from Sagittarius A*. The black hole itself would still be invisible, but its surroundings would blaze with energy as gas spiraled inward, heated to extremes, and released torrents of radiation across the electromagnetic spectrum. The galaxy would look familiar in outline, yet fundamentally altered in character. The difference would not be cosmetic. It would be environmental, structural, and deeply consequential. In this alternate present, Sagittarius A* would behave like an active galactic nucleus. Matter falling inward would form a dense, luminous accretion disk, converting gravitational energy into intense light. X-rays and ultraviolet radiation would dominate the inner galaxy, accompanied by high-energy particles accelerated to near light speed. Powerful outflows would emerge from the central region, driving winds and possibly jets far above and below the galactic plane. The heart of the Milky Way would no longer be quiet. It would be loud enough to be felt across tens of thousands of light years. Radiation is the first and most immediate consequence. High-energy photons do not remain politely confined to the galactic center. They travel outward, interacting with gas, dust, and planetary atmospheres. In the inner regions of the galaxy, this radiation would strip electrons from atoms, ionizing vast volumes of space. Molecular clouds would be heated and dispersed. Star-forming regions would struggle to survive in the presence of such persistent energy input. Planetary systems would fare no better. Worlds orbiting stars closer to the center would be exposed to a constant bath of radiation far beyond anything experienced today. Atmospheres would erode under relentless particle bombardment. Surface chemistry would be disrupted. Protective magnetic fields could delay damage, but not indefinitely. Over time, even resilient planets would be stripped bare, transformed into sterile remnants. The effects would not stop at the inner galaxy. Energetic outflows can propagate far from their source, pushing against interstellar gas and altering its distribution. Shock fronts would compress some regions while evacuating others. The delicate balance required for stable star formation would be disturbed on a galactic scale. Some regions might experience bursts of starbirth triggered by compression, while others would be starved of gas entirely. Our own location, far from the galactic center, offers some protection, but not immunity. Even at tens of thousands of light-years away, a fully active Sagittarius A* would change the background radiation environment. Cosmic rays would become more abundant. High-energy photons could reach the outer disk, subtly increasing mutation rates and stressing biological systems. Life might persist, but under harsher conditions, its margins narrower and its resilience constantly tested. This counterfactual scenario exposes how fragile habitable conditions truly are. Life depends not just on a planet's distance from its star, but on the broader galactic environment. Stability is layered. A quiet star matters, a calm neighborhood matters, and a restrained galactic center matters as well. Remove any one of these, and the window for life narrows dramatically. The contrast with our actual experience is striking. Sagittarius A asterisk today emits only faint radiation. Its outflows are weak. The galactic center, though energetic compared to interstellar space, is not hostile on a galactic scale. This restraint allows molecular clouds to survive, stars to form steadily, and planetary systems to evolve without constant external disruption. The galaxy feels ancient and settled because, for now, it is. This realization introduces a subtle existential vulnerability. The conditions that allow life are not guaranteed by default. They are the result of circumstance layered upon circumstance. A different inflow of gas, a different dynamical history, and the Milky Way could have been far less hospitable. Nothing in the laws of physics demands a quiet supermassive black hole. Silence is contingent, not necessary. Yet within this vulnerability lies relief. The fact that Sagittarius A asterisk is quiet today is not trivial. It is a profound piece of good fortune. The same object capable of reshaping the galaxy currently allows it to remain stable. The same gravity that could drive destruction now anchors order. This contrast deepens appreciation for the present rather than diminishing it. Perspective expansion follows naturally. Our instinct is to think of threats locally: asteroids, stellar flares, climate shifts. The active galactic center introduces a larger frame. It reminds us that habitability is a galactic-scale phenomenon. Life unfolds not only under a star, but within a galaxy whose large-scale behavior sets the boundary conditions for everything smaller. This broader view does not imply that life elsewhere is rare, but that it is conditional. Other galaxies host far more active cores. In those environments, life may be confined to outer regions, delayed, or suppressed entirely. The Milky Way's relatively gentle history may be one reason it remains fertile. Our existence becomes not evidence of cosmic generosity, but of balance achieved over long time scales. Imagining an active Sagittarius A asterisk also reframes fear. The danger is not sudden annihilation, but slow erosion. Life would not vanish overnight. It would be pressured, constrained, and reshaped. Habitable zones would shrink. Evolution would proceed under constant stress. Complexity would be harder to sustain. The galaxy would still exist, stars would still shine, but the conditions for long-term biological richness would be compromised. This thought experiment sharpens awareness of how interconnected cosmic systems are. The behavior of a black hole influences gas dynamics. Gas dynamics influence star formation. Star formation influences planetary systems. Planetary systems influence the possibility of life. The chain is long, but unbroken. Change the first link, and the consequences cascade outward. Returning to reality brings a sense of quiet relief. Sagittarius A asterisk is not active today. The Milky Way is not bathed in lethal radiation. Planetary atmospheres remain intact. Life has had time to experiment, adapt, and persist. The galaxy's center, though powerful, is restrained enough to allow complexity to flourish far from it. This does not eliminate risk. The future remains open. Over millions of years, conditions will change. But cosmic timescales are long, and life operates within windows carved by chance and physics alike. The present calm is one such window. Imagining an active galactic center ultimately expands perspective rather than inducing despair. It clarifies how much has gone right without suggesting that it was designed to do so. The universe does not protect life intentionally, simply allows pockets of stability to emerge. We happen to inhabit one. Sagittarius A*, in this light, becomes a measure of scale rather than a source of fear. It shows how close the Milky Way could have been to being a harsher place, and how narrow the margins of habitability can be. That awareness does not diminish the universe. It deepens respect for it. By comparing what is with what could have been, understanding sharpens. The calm at the galaxy's center is no longer background. It is context. And within that context, life's presence feels neither miraculous nor trivial, but precarious, temporary, and all the more meaningful for having emerged in a universe where such outcomes are possible, but never guaranteed. Seen in isolation, Sagittarius A** can feel like an exception. Unusually quiet, oddly restrained, sitting at the center of a galaxy that appears calm and long-lived. But when the view widens beyond the Milky Way, a deeper pattern emerges. Supermassive black holes are not rare anomalies. They are nearly universal features of large galaxies woven into their structures so consistently that it becomes difficult to imagine one without the other. Wherever astronomers look, massive galaxies host massive black holes at their cores. Spiral galaxies, elliptical galaxies, even galaxies caught in the aftermath of violent mergers all reveal the same pairing. More striking still is how tightly linked the properties of these black holes are to the properties of their host galaxies. The mass of a central black hole correlates with the mass of the galactic bulge. The speed of stars orbiting the galactic center reflects the black hole's influence. These relationships are not loose trends. They are precise enough to suggest long-term coordination rather than coincidence. This universality forces a shift in perspective. Black holes are not merely passengers carried along by galaxies. They are regulators, participants in a feedback process that shapes how galaxies grow, evolve, and eventually age. The galaxy feeds the black hole, and the black hole responds by feeding energy back into the galaxy. Over cosmic time, this exchange produces balance. The mechanism behind this regulation becomes clearer when viewed across many systems. In young gas-rich galaxies, rapid star formation and frequent mergers drive large amounts of material toward the center. Black holes in these environments grow quickly, becoming active and luminous. Their energy output heats surrounding gas, preventing it from collapsing too rapidly into new stars. Star formation slows. Gas is redistributed. Growth moderates. As gas supplies diminish, black hole activity subsides. The galaxy enters a quieter phase, forming stars more slowly and steadily. The black hole remains massive, but dim. This cycle repeats at different scales and times, producing galaxies that neither burn themselves out too quickly nor remain stagnant indefinitely. This pattern gives black holes a paradoxical role. They are agents of limitation. By preventing runaway growth, they help galaxies persist longer and evolve more coherently. Without this regulation, many galaxies might convert their gas into stars too rapidly, leaving behind exhausted systems incapable of sustaining structure or complexity over long periods. Sagittarius A* fits neatly into this larger story. Its present quietness is not abnormal, but characteristic of mature galaxies like the Milky Way. Our galaxy is neither young nor starved. It sits in a middle age where growth continues, but at a measured pace. The black hole's subdued state reflects that maturity. Authority emerges not from any single observation, but from synthesis across millions of galaxies. When the same relationships appear repeatedly across different environments and cosmic eras, they point to underlying rules rather than accidents. Supermassive black holes and galaxies appear to co-evolve, each shaping the other through long feedback loops rather than short bursts of dominance. This realization brings intellectual coherence to what might otherwise feel chaotic. Galaxies are not random assemblies of stars. They are systems governed by regulation, constraint, and interaction across scales. The black hole acts as a stabilizing influence, enforcing limits through energy rather than force, through feedback rather than destruction. Understanding this also reframes how cosmic violence is interpreted. Active galactic nuclei, with their brilliant radiation and powerful jets, are not signs of disorder. They are transitional states, moments when a system corrects itself. Energy released by the black hole prevents further collapse, restoring balance rather than annihilating structure. Sagittarius A* appears modest by comparison, but its restraint is part of the same process. It no longer needs to regulate aggressively. The Milky Way has already settled into a stable configuration. The black hole's role now is maintenance rather than intervention. There is meaning in this universality. The same principles apply whether one examines a distant quasar blazing at the edge of the observable universe or the quiet center of our own galaxy. Physics does not change its rules for scale or familiarity. Gravity, energy, and feedback operate everywhere, shaping outcomes consistently across space and time. This perspective also dissolves the temptation to anthropomorphize. Black holes do not intend to regulate galaxies. They do not seek balance or stability. They respond mechanically to conditions around them. Yet from that mindless response emerges structure that appears almost purposeful in its consistency. Order arises not from design, but from interaction. For human understanding, this is a powerful lesson. The universe does not need foresight to produce coherence. It requires only rules that apply everywhere and time enough for those rules to express themselves. Galaxies evolve not toward goals, but toward states permitted by physics. Supermassive black holes help define which states are reachable. Placing Sagittarius A* within this broader pattern removes any sense of isolation. Our galaxy is not special because it hosts a black hole. It is typical. What feels unique is only our proximity and ability to study it in detail. The same processes shaping distant galaxies are at work here, quietly and continuously. This universality deepens awe without invoking mystery for its own sake. The Milky Way is not a fragile exception in an otherwise hostile universe. It is one instance of a common outcome produced when mass, gravity, and time interact under familiar laws. Life arises not because the universe bends rules, but because those rules allow stable systems to exist long enough for complexity to emerge. Intellectual coherence follows from this realization. The story of Sagittarius A* is not a side note. It is a local chapter of a cosmic narrative written across billions of galaxies. The same feedback loops that once shaped distant quasars also shape the environment in which our galaxy matured. This does not diminish the significance of our home. It contextualizes it. Understanding that the Milky Way follows the same rules as everything else does not make it less remarkable. It makes it intelligible. And intelligibility at cosmic scales is itself extraordinary. By zooming out, the black hole at the heart of the Milky Way becomes more than an object of fascination. It becomes a point of connection, linking local observation to universal behavior. Sagittarius A* is quiet now, but its role is clear. It is part of a vast pattern in which black holes and galaxies grow together, restrain each other, and settle into long-lived forms. In recognizing that pattern, the universe feels less arbitrary and more structured. Not kinder, not harsher, but consistent. And within that consistency lies a form of meaning that does not depend on centrality or significance, only on understanding. At the end of all measurement, black holes remain thresholds rather than destinations. Sagittarius A* can be weighed, located, tracked, and tested, yet it still marks a boundary where understanding thins and mystery begins again. This is not a failure of inquiry. It is a feature of how reality is structured. Some regions of the universe can be described with precision, while others exist as limits, places where our best theories point towards something real but cannot follow it all the way through. Black holes sit precisely at that edge. Outside the event horizon, the universe is legible. Motion follows equations. Time dilates in predictable ways. Light shifts frequency according to gravity's depth. Every observation near Sagittarius A* reinforces this order. Yet the same equations that succeed so completely also predict their own breakdown. At the horizon, paths through space-time narrow. Beyond it, prediction ends. The singularity, if it exists, is not merely unseen, it is undefined. This duality is unsettling because it confronts a deep human expectation. That knowledge, once earned, should continue smoothly inward. Black holes refuse that continuity. They reveal that understanding can be precise up to a boundary and meaningless beyond it. The universe allows islands of clarity, surrounded by oceans we cannot chart. What makes this boundary important is not what lies beyond it, but what it teaches about the nature of knowing. Science is often imagined as a process that erases mystery. In reality, it rearranges it. Each discovery replaces a vague unknown with a sharper one. Sagittarius A* did not eliminate mystery at the galactic center. It refined it, turning a hazy absence into a well-defined limit. This refinement carries epistemic humility. The black hole forces acknowledgement that reality is not obligated to be fully transparent. The laws that describe gravity with astonishing accuracy also imply that there are places where those laws stop speaking. Accepting this does not weaken science, strengthens it. By clarifying where confidence ends and curiosity must change form. There is also an identity shift embedded in this realization. Humanity's role is not to stand above the universe, mastering it piece by piece, but to participate in an ongoing dialogue with it. We ask questions, reality answers some, deflects others, and withholds a few entirely. The presence of limits does not diminish human intellect. It defines the arena in which that intellect operates. Black holes highlight this relationship starkly. They are not puzzles awaiting clever solutions in the ordinary sense. They are reminders that some aspects of existence may require new frameworks altogether, or may never be rendered fully accessible. The event horizon is not just a physical boundary, it is a conceptual one. This is why awe persists even after explanation. Understanding how Sagittarius A* influences stars does not make it less profound. It makes the remaining unknowns sharper. The singularity, quantum gravity. The fate of information, these questions remain unresolved, not because we have failed, but because we have succeeded in pushing inquiry to its edge. There is a temptation to see these limits as temporary obstacles, placeholders until future theories arrive. Perhaps some are. Yet it is equally possible that certain boundaries are permanent, reflections of how observers embedded in spacetime can interact with spacetime. Not every mystery is guaranteed resolution. Some may simply mark where perspective runs out. This possibility reframes ambition. The goal of understanding is not total conquest, but meaningful engagement. Sagittarius A* teaches that clarity and mystery are not opposites. They coexist. The same object can be precisely characterized and fundamentally unknowable at the same time. Emotionally, this realization can feel disquieting. Humans seek closure. We prefer stories with endings. Black holes deny that comfort. They offer coherence without completion. They insist that the universe is deeper than any single narrative can contain. Yet there is something stabilizing in this denial. It removes the burden of final answers. It suggests that meaning does not depend on total knowledge. One can live within a universe that is partially opaque and still understand enough to navigate, to wonder, and to act. Sagittarius A* also dissolves a subtle illusion about scale. The limits it represents are not distant in principle. They are immediate. The event horizon is not a metaphor. It is a real surface in spacetime where cause and effect reorganize. The fact that such boundaries exist within the same universe that allows stars, planets, and life implies that reality is layered rather than uniform. This layering matters. It shows that the universe accommodates both predictability and mystery, both law and indeterminacy. The presence of black holes does not undermine order. It contextualizes it. There is a quiet ethical implication here as well. Humility before limits fosters care in interpretation. When scientists acknowledge uncertainty, they do not weaken trust, they deepen it. Sagittarius A asterisk stands as an example of restraint. Just physical restraint in its current quiet phase, but intellectual restraint in how it is understood. The black hole does not invite reverence because it is powerful. It invites reflection because it marks a boundary where power, knowledge, and mystery intersect. It reminds us that the universe does not exist to be fully explained, only to be engaged honestly. As the arc of understanding stretches forward, new instruments will see closer. Theories will sharpen, and some mysteries will recede, others will not. The event horizon will remain a horizon, a line beyond which inference gives way to silence. That silence is not empty. It is full of implication. It tells us that reality is larger than explanation, that existence exceeds description. In a universe without such boundaries, curiosity would have an endpoint. Black holes ensure that it does not. The lasting contemplation Sagittarius A inspires is not fear, but perspective. It teaches that knowing where understanding ends is as important as knowing where it succeeds. It reframes intelligence, not as domination, but as orientation, knowing how far insight reaches and where wonder must take over. At the heart of the Milky Way, something exists that can be measured to extraordinary precision and yet never fully known. That coexistence is not a flaw in human knowledge. It is one of its defining conditions. Sagittarius A asterisk does not close the story of the universe. It keeps it open. And in doing so, it reminds us that meaning does not arise from final answers, but from the ongoing encounter between what can be understood and what remains just beyond reach.